Okay, thank you very much for the invitation. I'll report on our work on how to use quantum computers for biomolecular free energies. And My name is Matthias Christandl. I'm a professor at the University of Copenhagen, and this is part of a larger collaboration with ETH Zurich, MIT, and also Novo Nordisk. You'll find the link to the archive down here in the bottom right. And I first want to tell you a bit about the project and the team. Um, so it's really a project that already from the title of how to use quantum computers for biomolecular energies spans the whole area from health sciences to quantum computing. So um, and I believe this is very hard to do if you have just people from the two ends. So what you really need for such a project is a sequence of experts that can cover from one part to the other. So we have Aaron, who actually is in the audience. Hi, Aaron, who is our quantum algorithms expert. Well, I'm also working in the area of quantum computing. Then we have Markus Reyer, who is a quantum chemist, so small quantum systems, you can say in some sense, and Troy van Voorhees from MIT as well. And then Gemma Solomon, also on the quantum chemistry side. And now it gets larger, the systems. Anders Kroh is a machine learning expert, but on biomolecular structures. And Christandl Larsen is an expert on proteins, so large biomolecular structures. And Jesper Falkenhoff-Borg is our Novo Nordisk, so Novo Nordisk, the company representative. We're being funded by a number of funding agencies. One is Novo Nordisk Foundation. And the Novo Nordisk Foundation funds a large grant that I have. It's called the Quantum for Life Center, and also the Novo Nordisk Quantum Computing Program at the Niels Bohr Institute in Copenhagen. We're also part of the Quantum for Bio project by Wellcome Leap, which financed part of this project. But with a bunch of professors, you're not going to run a project. So we had a team of more than 20 people working on this for basically 2 years. And you see them here from our now it's CQT is of course a quantum unit. So let me highlight our quantum colleagues. So that's Marek Miller, who's a postdoc here. Freek Witterin is also a postdoc here. Li Liu as well. And then we had 2 PhD students involved from here, Dylan Harley and Jakob Günther. But we're very closely interfacing with the entire team listed here. Now, the project is about the question of how you can investigate whether a drug candidate, and I think as a drug candidate, you should think of it as a small molecule, like the one here. Maybe can you see my pointer? Can you see this laser pointer? Yeah.
Yes,
So
we
how
can
these
see it.
small molecules interact, or whether or not they dock to a large molecule like a protein. So that's the question we want to try to answer. And first we have to understand the questions. That's why we need all these experts. And and as you can imagine, everything is built from atoms here. So the interactions between the drug candidate and this big protein, those are in some cases have very strong quantum mechanical features, and therefore there is a hope of describing them or using quantum computers to better understand those systems. So there will be, at some point in the project, this is just an overview, there will be a zoom in on what we call the quantum region or QM region. And the other region is, we would call it the classical region, but traditionally it's called the MM region for molecular mechanics. Then you take that part and you investigate its Hamiltonian, and you want to put this on a quantum computer. So you want to map an embedded quantum problem to this qubit Hamiltonian and then discover or compute the properties on a quantum computer. The challenge in this setup, and that is you will discuss more, is that the molecule is not uh, the protein is not a fixed structure. It sort of like moves around and wiggles around, and this means that actually this is a thermodynamic problem. So the thermal energy lets the molecule wiggle and explore many configurations. And in this sense, you actually don't need to compute like one energy, but you want to compute like an average, so like a free energy. And so we want to compute a Gibbs free energy, Helmholtz free energy, and this is sort of like the target. That is why the title, How to Use Quantum Computers for Molecular Biomolecular Free Energies. Okay, if you have any questions, just feel free to interrupt me. So the first thing maybe we need to understand is this energy versus entropy discussion, and we made a quadrangle, called it the biomolecular simulation quadrangle. So on the x-axis, you have the energetic complexity, and on the y-axis, you have the entropic complexity. So if you start on the, if complexity in both directions is small, you have really something that you can describe. Now it says single reference, single configurational. That basically means you can describe it with a rather uncorrelated quantum mechanical state, or an example would be like a water molecule. And if you ramp up the energetic complexity, but there's nothing somehow really wiggling around, right? Then you get to strong correlations. So without this configurational flexibility, and here you have the famous example you probably heard of, this FeMoco cofactor in nitrogenase that has been proposed as one target application for using quantum computers, and actually has become sort of like a benchmark for many aspects. So in some sense, when you have weak correlations, and many of these biomolecular systems, actually the correlations are rather weak. For instance, proteins or other bio structures, nucleic acids, lipids. Then somehow there's a lot of configurational sampling you have to deal with, and this is what our work focuses on. And of course, you can then also have this in the case where you have very strong correlations, and there's also examples for this. So we're discussing in this work, essentially we provide a tool to study, to explore the space here computationally and ab initio. And but we don't actually do runs on a quantum computer yet. And that is why sort of like our target example lies here in the top left. But we investigate in how far you can push it both to the top left and to the top right, so that you use quantum computers for that. So let's dive in more into the free energy part. So you here below I have an integral for you, and what you see here, it says like the Boltzmann constant Kb, then you have the temperature, then you have the logarithm. So this is really the free energy that you obtain from computing this partition function. And as you see the partition function, I will not go into too much detail, but you integrate over phase space, and then you want to get the energy right. So this is sort of like the energy of your nucleic of your configurations of the atoms. So if you think of a molecular structure, we should have said it here before. We're working in this Born. I will come to it also again later, but we will work in the Born-Oppenheimer approximation. So if you think of like these molecules we've been talking about, you should think of the nuclei as having a classical position in space, and here denoted by a capital R. And as you move them in different positions, the overall system has a certain energy, and we look at the ground state energy here because the electronic excited states lie above. Okay, so here is an example of a landscape. So an energy landscape where you can imagine, say, the landscape is on top of the possibilities for where the nuclei are, or the nuclei positions. And so, for instance, here, if we now look at this graph, yeah, and so what you have to do is you have to integrate this partition function, and then this way compute um, compute the free energy. And what you see here is that you have,
Sorry, so
yes,
quick question. NS is the number of nuclei.
yes,
Okay. Okay.
yeah, the
I
number.
I have another question. So if God gives you this E ground state quantum as a function of R, then
Yes.
the problem is easy in some sense
Um,
for, I don't know, a molecule
Well,
of
you still have your sampling, you still have the sampling, you still have the sampling problem. You still have to sample over it. But yes, so yes, so if the goal of the game is to sample this energy landscape. So you want to get a good approximation to this energy landscape.
but
But the molecule is very, very large.
Mhm.
So you are not able to sample this directly. So we'll come to that. We'll come to how we're going to do this. Okay. So, but for the moment, you know, um, for the moment, just this is a little bit of an abstract fly-in, reminder of your thermodynamics, that you have a free energy, and that it has an energy landscape you can sample. And how we're going to do this, we will see in a bit.
And another question, I mean, if you wanted, I mean, you have some approximation here that you're using the ground state energy, right? I mean, if you wanted to be more
Yes,
precise, you would have had to trace over all the degrees of freedom of the,
that's right. Yeah. So my understanding is that this is not the problematic part of the approximations.
because you have a spectral
Yeah,
gap or something like
yeah,
that.
because it's sort of like the electronic gap is really quite large compared to everything else.
Okay, thanks.
All right. Um, Yeah, so as you see, there's some current approach where you basically deal with it classically. So, and of course, there are certain, I'm not going to go into references now, but there are certain parts of where you can put also more quantum information, or like more information about the quantum mechanical effects into this game. But essentially, it's heuristic forces that are being used to understand this potential energy landscape. And the idea, of course, is to enhance this with quantum mechanical information, more quantum mechanical information. All right, yes. So here are there are two main challenges. So the first is, so as you saw, it's an ab initio problem that we're trying to solve. So we're really like trying to compute this. To compute this free energy, and then thereby the free energy differences or the free energy path and so on. So first of all, there's way too many points to compute, like way too many. That's one of the problems, and The second problem is that even if you could compute, well, or the problem is to compute a single point. Right? And the single point computation is if you want also the problem that people have faced in when they treat Fimoco or so here somehow you have these two problems on top of each other, and you're trying to understand how to deal with it. So the two solutions for the problem is that you're using basically you're starting from these classical models, and then you're using machine learning to fold in additional, more high precision data into the problem. And the second point is that you have these two large molecules. So you're going to break it down into this quantum region, what I already alluded to in the beginning. So these are the two things we're doing. So I will now show you the overall setup and then go into more details. Okay, so the overall setup looks like this. I mean, to give you like the atoms have like there's thousands of atoms, right? Just to give you an idea. So it all starts. So this is to be read from the left. So it all starts with the so-called structure preparation equilibration. Okay, so essentially, the first thing you have to understand is roughly how does your protein look like. Okay, and so a structure will be prepared, and it will be it will be found out where is sort of like the energetic minimum. How does it roughly look like? So you take this equilibrated structure. This in itself, for any given case, is quite a lot of work. So this takes months for a PhD student postdoc to work on these things for specific cases. Then you want to compute these free energies, and I'll say more about it. But really, you were only interested in free energy differences. So if you're trying, and there's a lot of error cancellations, right? So essentially everything is an approximation, but a lot of errors cancel. And one of the techniques one uses here is free energy perturbation. That's the name of the method. And so if you think about it this way, that there is sort of like a standard way of doing it called the method. So like a classical method where everything is classical forces. And maybe these classical forces or these forces between the atoms that you postulate, maybe they're fitted from some other computations. So they are like informed maybe from some quantum mechanical data, but you really take them into account like that. And then you can already compute with like these standard methods, the first free energy perturbation. Then what you would like to do is successively refine this. So it becomes better and better or more accurate or takes more quantum effects into account. And that is what we're going to do. So, and this is sort of like what the whole path here on the right. Okay, so you want to go down here to the next level refinement and then to the final level refinement. And so what you do is you basically take this around here, around this loop to get this free energy perturbation. So essentially, you can imagine that in this first free energy perturbation, it is like so you're sampling this high dimensional space, not by just some random points, but you sample it. I think in mind is really a godicity from thermodynamics. You start somewhere and then you let it move around with the forces, and it just explores that space. Okay, so you get a trajectory. So it's being thought of as a trajectory. And so you have this trajectory. That's why it's called molecular mechanics, MM. So then you take from this trajectory, the trajectory has like many points. You select some snapshots. Okay, so it's like pictures in between of how the structure looks like. And then you also select a region of interaction or a quantum mechanical region um, that you want to treat quantum mechanically. Okay. Then
But so a snapshot is what? Is a trajectory or a part of a
no, no,
trajectory?
a snapshot is a configuration of the nuclei. Okay,
Okay.
so when you move your trajectory, you're exploring different configurations of nuclei, right? And now from this
I see.
different configurations, you take out several. I mean, to make it concrete, it's the selection for which we are doing this quantum refinement. The selection is roughly 4,000. Okay? So roughly 4,000 snapshots. Okay. So this already is kind of interesting because whenever someone gives you a time estimate for using a quantum computer, at that point in time, you can multiply it by 4,000. Or you can, which significantly blows up the time for using quantum here.
Wait, but you have 400 different Born-Oppenheimer approximations, and you want to explore these, or no? Or
Everything is in the Born-Oppenheimer approximation. Okay, so
okay,
everything I'm saying is like you have classical nuclei or you have like fixed nuclei positions.
you
Okay,
have 400 of these.
4,000.
4,000, okay.
Well, I mean, I have more, right? I have more, but I select
Uh-huh,
like 4,000. Okay. If you
okay,
think of selection, you think of 4,000. That's a good.
okay.
Okay. So then, because right, what you want to do is you want to refine. You want to refine your. You want to refine. So you basically have a very crude energy landscape, and now in the relevant part of that energy landscape, you want to make improvements to it. Okay, so you want to find out, so and those improvements are basically energies and derivatives of energies. And then you want to find like improvements. And then what you want to do is you want to fold those improvements into like you want to get
Mhm.
an improved energy landscape from that. So you take your energy landscape, you take some path through it, you select some snapshots and a quantum region, then you are computing better data for this part. We can discuss how to do that, right? And then you're gonna fold it, right? You're not gonna throw out the other model because you have many more data points, etc. So you are going to improve it by somehow training in what we call ML1 force field. Okay. And then once you have that training done, this is down now here, right? So the training basically is in a loop. This is called active learning. It's an active learning loop. So you kind of like learn and then you check, oh, did it improve? And maybe you have some indicators that tell you like, oh, here the uncertainty was high. And then you go compute some more and train some more and hopefully it converges. Okay. And then you get your first improved free energy. Okay. Right. Then so that's the first way. Then what you can also do because this will still be pretty big. So if you think of um, this first level here, it's actually a DFT, so it's a quantum method, but it's not the wave function quantum method like we usually like to do it. So you can refine this by an inner core. I'm gonna have more graphs for that. And so you also have to, from this quantum region, you can now try another improvement, which is this free energy perturbation 2. So you take a smaller core, and this you treat in the way that
Mm.
quantum computing people like to treat systems, and you get some refined things. Then you would like to do a loop like this again. Now, this turns out to be more difficult because you only have access to energies at the moment. So here something else is used. It's called transfer learning to obtain this ML2 force field and then to obtain this free energy perturbation. Okay, so that's a rough setup that we're playing with and that we've been built, that has been built. So it's a large computational, or how do you say, software package in some sense, if you want. And we call it free quantum for obvious reasons.
Thank you.
Right. Yeah, and this one here, you see, this is where quantum computer is being slotted in once we have it to sufficient quality. All right.
Oh, so
All right.
excuse me, can I ask a question? Uh,
Sure.
how you generate the snapshot using MC or molecular dynamics or other way?
Say again, how?
How can you generate the snapshots? You mentioned there are 4,000 snapshots you generated.
Oh, how they're generated, how they're being selected.
Yeah, based on what method?
I actually would have to go back and ask my experts. This will actually be for many parts of the project a little bit like that. There's so many parts, so many people involved. I'm not the expert in all of the details. I can try to answer this question so probably part of the answer will be already in the paper. So if you look for that in the paper, and apart from that, I'm very happy to guide you to the right expert to answer this question for you offline later. That's okay.
Oh, okay, thank you.
All right. I tried to understand the free energy perturbation part though. Okay, so bear with me, it took me some time. So here's the partition function, like how we like to write it, right? Trace x minus beta h of r are in nuclei, but I already mentioned it's only the ground state energy that's relevant. So the approximation from before is fine. We are interested in computing free energy differences, and the integral is so vast that that the problem is that if you're trying to compute this one here and this one here separate, then you will make too many errors. Like the error will be too large. So you have to somehow, you cannot compute these two big numbers and subtract them. This doesn't work, apparently. Like whatever decades of research has shown. So the basic idea of free energy perturbation is to make a telescoping sum along the coordinate. Okay, so you can imagine that maybe there is, bound, unbound, and now you imagine that you don't know exactly how it bounds, but you maybe have some distance. Okay, so molecule here, and there's some distance. And so you make a telescoping sum. Okay, so like, I don't know, k equals 0 is lambda 0, right? It's the bound one, and then the other one is, so you do a telescoping sum, and then you have lots of these differences, and for each, the sampling problem is similar. Right? So you have a sampling problem for this and this, so it's similar, and for this and this, and they're similar, and so on. In this way, somehow you get a lot of error cancellation. And of course, you're not going to still compute the differences, but then it's like some ratios in these that will have some acceptance ratios and so on. So they have clever ways of computing these delta G's when the sampling is not very different. That's I think the main idea here. And and so that's the main basic idea. Maybe you can try to remember that, the main basic idea of how to compute this free energy perturbation. But then, of course, something else will be going on, and that is called alchemical. So first of all, that we want to compute this in a realistic system. And the realistic system will be a system in water. So now imagine I give you these big molecules, and then on top of it, I put water around them. Okay, so one problem is that you have this like pocket where the molecule is going to dock. Well, maybe before there is some water, and then later on there is no water. So it's like it's a mess. So so they have a very clever way, and it's called alchemical, right? Because it's not, it's an artificial way of fixing it, the problem. And it works like this, that you define basically your Hamiltonian as you have the protein, you have the ligand, right? This drug molecule, and there is an interaction that they have, right? So, right, it's like imagine the protein in vacuum, right? Imagine the ligand in vacuum, but now you put them both together, right? There will be some interaction. So you take them, these three separate, and then you can, of course, switch on and off the interaction. And if the interaction is off, it will be like the sum, right? The free energy will be like the sum of the free energy of this one and this one. Like as if they were separate. And if it's on, then it's your desired system. So this way you can sort of like go from one to the other, and you can do the following. So if you're now interested in the solvated binding, so you're interested in the binding problem in water, right? So like in solution. Then, and now let me see if I can still get this. So you want the solvated complex, right? You want to know what is the solvated complex minus the solvated protein minus the solvated ligand. That is what you're interested in. And so what you do is you add the unsolvated ligand, or you subtract it here and you add it here again. And then what you see here is that you have a situation like before. You have the ligand in water, right? And you switch on the interaction with the water. Okay, so that's your alchemical computation. And here you have the yeah, okay, so partially solvated binding. Okay, so well now I forget exactly how it is. So then we do telescoping with okay, so you basically yeah, you basically now treat this ligand solvation problem separately, and you treat this partially solvated problem separately, and each of them so each of them you treat with this telescoping from above. Get it roughly right. Okay. So there is also actually a nice graph in one of the companion papers of how this works. But essentially the idea is that you use this alchemical part to handle the water. Okay, that's around this molecule with switching on and off. And then you still use this telescoping sum idea of computing the solvated binding. What happens in practice when you do this on these molecules is that there's essentially already like the software for parts of these things is already existing. So you're using like some standard tools that that people use for obtaining these energy differences. Yeah.
So, quick context for computer scientists. The water is important because water molecules are changing the force field of the molecule and the protein, of the ligand and the protein. So that's why you want to take into account
I mean, you
water
want to take into account
molecules.
water because the experiment you're going to do, or the if you imagine this in your body, there'll be water around it.
So reality as
that's
water.
why you
You
want to do
to
it. And in principle, right? In principle, you could, of course, you well, I mean, what they will do is they will actually put these water molecules there, right? So in addition to this protein, right, I've shown about the protein structure and so on,
Hmm.
but there will also be water molecules wiggling around.
Hmm.
So you want to somehow deal with it, and apparently this and there's so many, apparently the way to deal with it is to somehow do it this way, that you take the structure and you want to switch on the you somehow don't want to. I think you don't want to start having to discuss like how the ligand like pushes out the water molecules out of this pocket. Just
Hmm.
imagine, right? So it's like you don't want to discuss that. So, and I think this is what the switching on and off allows you to do. So, right in the
So is
bound
this
situation,
lambda 0 in one parameter or is a
yeah,
continuous?
exactly. So, yeah, I should have, I wanted to put it on the slide. There is a nice picture in one of the other papers I can sent to you later. So you don't want to have this pushing out process, right? You want to discuss a situation where it's unbound, meaning, say, in the pocket there is water, and a situation where it's bound, meaning in
Hmm.
the pocket there is no water. And you somehow want to get this water discussion out of the picture, okay? And that is somehow why you do this alchemical path here. But yeah, and then once you have this alchemical path, problem is, as you imagine, you're back to kind of like the normal binding problem. But I just wanted to show to you that there is a complexity to this entire machine, or to this entire problem that sort of like goes beyond what we usually think about in quantum computing.
And one last question, what is S in the
So,
summation of a telescopic sun?
yes.
What is S?
Sorry, what is S or?
Yeah, like this.
Yeah, I just discretized it. I mean, I just took some.
Okay, okay, okay.
Look, this is if I ask my colleagues to explain this to me, they'll just point to a textbook. So so it's like this is what I, a quantum computing person, extracted from reading textbook chapters in this area. It might well
Okay.
be that, and it was not so easy to convince everyone that this might be the consensus opinion. Yeah, there's a
Hmm.
question.
Hmm. Hmm.
Go ahead, just ask.
Hi, can I ask a question? Can you
Yes.
explain what this co reaction coordinate method is?
Um, I I don't think it's called the reaction coordinate method. Um, I think it's just um, that you have to imagine that you are sampling, right? Reaction coordinate. I think you should think of as this distance of these two objects. So, right, you want to kind of like understand when you put the two things closer, does the energy or the free energy, does it go up or does it go down? Right? Right. So if I have two molecules and I have them far apart, or I bring them, and when will they react? When will they bind? Well, they will do that when the energy goes down, or the free energy goes down when I bring them closer. I think that's why it's called a reaction coordinate.
Okay, I see. Thanks.
Yeah, but it's not. Maybe I go back to this picture here. Just think about it as the x-axis here, or like, this is this high dimensional thing. Okay, excellent. Figured. Yeah, okay. So the machine learning, yeah, I mentioned this maybe in passing. Just one slide on the machine learning. The machine learning potentials are typically trained on energies and forces. For us, for this transfer learning, the energies are sufficient. And this transfer learning is used in order to leverage the few energy data points, and with few, I mean 4,000. Okay, so you want to like that you in the future can expect maybe from quantum hardware. My understanding is that if you have fewer than a few thousand, then it will be hard. Then it will be very hard to do anything. So that's why, somehow thousands is the order of magnitude here that you will need. But it's possible, and of course, like we use these traditional chemical methods, it's possible to train these force fields, and this graph is supposed to show some convergence in some of these cases we looked at. But I'll say more about that later. I wanted to say a bit about this quantum embedding. So now in this pipeline, you see that here is where a quantum computer will come in. Okay, that's the unique part for this project where quantum computer enters. But let me turn it around. If people talk about quantum advantage for biology, if they have something like drug discovery or something like that in mind, the rest of the stuff around it will be necessary. So you will, and interesting, I think, is that this stuff around does not exist black box. It's not like there is a software package and the quantum computer comes along. So you have to build it. And that is what we did. So we built basically the enabler for a possible quantum advantage when the right quantum hardware at the right quality level comes along. Okay? So this is one way of understanding this project. So building everything around it and understanding what you need and what you need to do here as well. Okay, so I said thousands of atoms. They will not fit on a quantum computer. Well, in principle, they might. Here's a very interesting sentence. In principle, they might, but well, we'd be too far in the far future. Okay, so maybe not relevant. Our software not relevant anymore in 100 years. So, but it's also not necessary. Okay, most of this protein complex is essentially it's classical. You can perfectly treat it classically. It's not necessary that you use a quantum computer to represent all of these things. So you shouldn't do it. You should only do the things that are actually necessary because quantum computers are kind of scarce thing. So you out of this molecule, you carve out this quantum region, QM region. Maybe you should think of the region where they interact. I think that's the best part. Think about it that way. You should think of the molecule as being small. So if you think of this quantum region, you should think of the interaction region plus the entire small molecule because it's small. And then this small region, now I forget actually how big it is, but it will still be too big. Okay? For the coming decades, it will be too big to put on a quantum computer. So this quantum region, you will treat with DFT, density functional theory. Okay, so you'll have to deal with that. You will have to do that, and then within that, okay, so here is my quantum region Hamiltonian is equal to the electronic Hamiltonian in the quantum region plus an interaction with the outside environment. Okay, and then you're gonna have the you're going to select some quantum cores, so smaller parts within your quantum region. And these smaller parts, so they will get some effective potential from the DFT outside. Okay, so the quantum region has an effective potential from the classical region around it, and the quantum core, 1 or maybe 2, or 3, or I don't know. In our case, basically 1. We have 2 methods for embedding. One is called bootstrap embedding and one is called Hutzinaga embedding. And both of those strategies, so Hutzinaga embedding only uses 1 core and the bootstrap has several cores. But let's say you have only 1 core, then you have the electronic part of the core plus an interaction potential from this DFT region from the outside.
Sorry, I have a question here. So
Mhm.
let's say if the interaction is decided from DFT, So can quantum computers still output a better answer than the classical computation method, for example, still based on DFT?
I'm sorry, say again.
So if the interaction is decided from DFT, can quantum computers still generate a better answer than the classical method?
I mean, the quantum computer can,
I mean,
yeah. Yeah. Okay. So imagine it this way: the molecule is very large, so the outside parts are classical, right? You can treat classically without making too large error.
mhm,
Then, as you're getting more quantum mechanical, as you're coming more to the interaction region, you want to take more quantum effects into account. But DFT has uncontrolled errors and is not always accurate. So some of these, so the innermost, the strongest quantum correlations, or maybe many small quantum correlations, you want to treat with the most accurate methods.
mhm,
Okay, you want to still home in some of the other quantum effects with methods like DFT applied to cases where DFT doesn't make so large errors. Okay, so think of this being classical, a little quantum, and then very quantum in the inside, or very correlated. Yeah, that's the picture. Okay, so two-level embedding. You could also have more levels, but I think this makes a lot of sense.
Related to that,
Yes.
is there any error bound you can put on these embeddings and calculations?
That's very good. Yeah, we'll come to that. I'll show you some data and then we can discuss.
Okay.
Okay. I mean, you mean rigorous kind of no, probably not. But
It's like an NP thing. I mean, you just get
yeah,
something and then you check if it's okay, if the patient dies or he recovers, maybe. Or
yeah, I'll show you. You'll see. Okay, anyway, so here actually I come with some quantum stuff. Maybe I should have said it before. Okay, so full problem, and then you have you do Born-Oppenheimer approximation, right? So it is kind of what I already started with. Maybe that wasn't so pedagogical. Here's your landscape again. Okay, but now let's say we all agree on that we have to compute the electronic energy. We have this many-body wave function, and we want to compute the energy for this many-body wave function, or we want to compute the ground state energy of an electronic configuration. This is maybe more standard now to some degree. This is now in the realm of quantum chemistry. In the realm of quantum chemistry, well, we would just say you want to solve the complete problem. Okay, solving the complete. Okay, maybe I should say it this way, right? What my slide before told you was the Hamiltonian. Okay, from the slide before, that kind of gave you the Hamiltonian. So there's like quantum chemistry people involved that give us the Hamiltonian, us quantum computer scientists. And they give us the Hamiltonian, and they have kind of like chosen a lot of things, right? They've chosen the snapshot, they've chosen the region, and they also chose like how to, it's still like a continuous problem with like L2 of R3, like Hilbert spaces, right? But they've also then already chosen a basis set. So they've truncated, so they made it into a discrete problem for us already. And they know that to treat this discrete problem, you can also easily imagine that for each of the atoms, you need essentially, for each of the atoms in these regions, you need, so the number of like places where the electrons can sit needs to scale basically linear with the number of atoms that you have. Right? So if I give you like 10 atoms and I want to discuss where do the electrons sit, I need, like, I don't know, 10 times X positions, right? So the number of, I want to at least one point say where this exponential explosion comes at all. It comes in this exact fact, okay? So the Hilbert space grows exponentially because you want to have the number of, because the number of modes is linear with respect to the number of electrons. So the exponential explosion with this region of the quantum core size, Okay, this is basically the exponential explosion. Right, so quantum pore size we treat well, and there we even there we got this explosion. Okay. And then there is ways, of course, of mitigating the explosion. And how do you do that? You say, oh, I'm just going to take one, I'm just going to do a Hartree-Fock approximation. Okay, which basically means for each, you have a bunch of orbitals, and in the orbitals you put an electron or you don't put an electron. Okay, already that is like NP hard to find out which would be the right one, right? If you look at it complexity theoretically. But that would be just one Hartree-Fock. There will be one configuration. Okay, so the chemists, they give you a list of orbitals or a list of spots where you can put electrons, and then you put the electrons, and each of these ways of putting the electrons is called a configuration. Okay, and that's basically it's a computational basis state. Put it here, and then you can say, like, rather than saying like, oh, I'm allowing arbitrary superpositions of all of them, which would be the full problem. They say like, okay, instead of like taking one, we take a set of them, a few of them, namely n of them. Okay, so if like I have n, so where you replace, so they let the configurations interact, and that is sort of like a superposition. So this way you get the hierarchy of approximations to the final problem, to the complete problem, which is then called full CI. Okay, CI stands for configuration interaction. And if you think of one Hartree-Fock Slater determinant as one configuration. That was in a nutshell wave function based quantum chemistry. Are there any questions? Sort of like running out of time. Okay, very good. So we want to use quantum computing because these approximations are still computationally challenging and there's no accuracy guarantees. We're using DMRG or tensor network methods as a proxy for full CI. So for this one up here, okay? There's a different story, but basically we're using this full CIs. So what are the biological systems? We have two systems. One is a benchmark system. It's some kind of complex used for testing purposes. And then we use something which has a stronger interaction, a transition metal called a ruthenium atom. And there is no benchmark data available. And the electronic structure is more challenging. So here is the full computational run. Okay, so let me remind you, this is like first principles. So there is a bunch of papers my colleagues have been writing on the stuff before you put a lot of quantum in. Okay, it's like you have to benchmark all the other parts of this pipeline. And here is the data, and I have a hard time judging it, but they have been very happy with it. So there is experimental data. I think this is quite remarkable. So there's someone who does an experiment and can compute minus 37.3 free energy, binding free energy, and then they do a computation with these models, and then they roughly hit this within error bars. Okay, and this was quite a complex system. So, I think congratulations to my colleagues. It's quite amazing. But the cool thing is that now this pipeline that they built, it can be applied to cases that lie outside of this realm of this model system where benchmark data and experiment and God knows what is available. And so we use this, and this comes out. So you see, again, I have a hard time judging this, but you can see that now there are more substantial changes, and that is expected because it's more quantum mechanical. And this work is just like you can think of the whole thing as one project. I just took the table from that paper where we then did these. These are different type of embedding methods. Okay, so I told you this is no embedding, the free perturbation 1. This here is the one where you do one embedding, and this is a DFT thing. And then this here is where you have this double embedding. And there's different degrees to how complicated you can make it. And here you see that, it's like in the hierarchy I gave you, it's kind of like from the bottom up. So it's like lower in the hierarchy, this is like singles, doubles, and then goes higher up. And FPT2 is like you put some additional perturbation theory on top, okay, to home in more correlations. It's called FPT2. Anyway, so PT stands for PT2 stands for second order perturbation theory. All right. Okay, yeah, so that's what it is. I think it's quite cool that it all works and that the results for the different methods are roughly consistent with each other. And I think this is quite impressive. Yeah, so what's the potential for quantum computing in the last couple of minutes? Well, I mentioned the energy computation of the core is carried out by quantum computers. The advantages would be that you get accuracy guarantees. Now, it's not completely clear how these guarantees will propagate through such a big pipeline, including machine learning and everything, right, from a computer science point of view. But certainly from the ground up, you get more precise energies. You can do it for larger systems and for more correlated systems. Now, we estimated.
What is the quantum algorithm you use?
Yeah, we'll come to that.
Oh.
So we're going to move from the idea then is that up here in this upper part, you can move from the left. So here at the moment, we were constrained here, or maybe a little bit on the right side of this actually. And then you can move here. So you can slot in this quantum computer. Okay. Okay, yeah, so we are going to use a quantum phase estimation. Essentially because we get some guarantees. So there's a lot of speculation in all of this, right? And how far. So here, I want to put us on firm footing as possible. And wanted to do quantum phase estimation. So if you do VQE, there's a lot of evidence it doesn't work. Also, it's again then heuristic, right? I think one of the main parts here now is that quantum computing can also offer some more first principles founding of this topic. So the main cost of phase estimation derives from the cost of Hamiltonian simulation. And in chemistry, we have an unstructured Hamiltonian. It's essentially just some gigantic matrix coming along from the chemists with many terms. They lead to a priori to very deep circuits. We try to stay as kind of like near-term realistic as possible, given that we are open, wanted to look into. I mean, of course, you can also slot a VQE machine into this. We just did not investigate. Okay, so you can do other quantum algorithms that you like into the pipeline, but we investigated this. So we use single ancilla quantum phase estimation in order to reduce the ancillas. Then in order to reduce the circuit depth, here is a small Trotter reminder of what a Trotter formula is, of how you take that. And you want to, as I mentioned here, in chemistry, some of the terms are small. So you don't want to fully treat them with Trotter. It's going to be too expensive in terms of circuit depth. So what you want to do is you can use this Q-drift method. The Q-drift method by Earl Campbell has randomizes. So it samples the terms at random. It's very nice. And what we did was use it for the small ones, for the small terms, and the big terms, home them in with Trotter. Okay, so like trying to home in the best of both worlds. This is on a Femoco benchmark, this little graph. And you see that for a few logical qubits, we beat what has been done before. And also in terms of this year's total cost up here, and this year is depth. Okay, so we improve what has been there before. But this is for the FIMOCO benchmark. The molecule we're looking at is not quite as expensive. And so no worries. Gonna get there. Yeah, and so we estimated the runtime. Okay, so we wanted to find out how good our algorithm is, and in terms of, and now what is the size? The size is this number of orbitals that I mentioned before. So you ramp up the number of orbitals, and if you reach a region like 60 to 80, from number of orbitals, so number of qubits you need is twice number of orbitals. Okay, so if you see like 20 orbitals, then it's like 40 qubits. And you want to be at basically very, very small error, right? So the error should be of order of like 1 over a number of gates in the circuit. So here you have the different methods, and you see that this partially randomized method performs quite well here, and also doesn't have ridiculous numbers. Okay, it's like 10 to the 5, 10 to the 6. Okay, in terms of depth. Of course, the total runtime, because it has more of a randomization, will be higher than than if you run a qubitization framework. But we think this trade-off might be still good in the near term, and it depends, of course, on the speed of the machine. I think what one of the main lessons for me was I didn't pay attention to the speed of the hardware until now. I think when you look at a problem like this and you need 4,000 data points, it matters because the ion traps and the neutral amps are just, or the ion traps certainly are very slow. So they're very slow. So in the future, a hardware-based, like a condensed matter-based platform, might be more suitable. But of course, at the moment, if you're talking about good error rates, the atoms are on the better side. So anyway, but I think this is what is very interesting about
But in any case, you're talking about fault tolerance, right? I mean, all these numbers are for fault-tolerant computers.
Well, I mean, what does fault tolerant mean? Fault tolerant will mean some kind of error level, right?
Yeah.
On the logical level.
Yeah, but we are very far away from the bare errors also in the atoms and the ions are very far away from what you need. So you will need error correction and fault tolerance.
Yeah, you will need error correction, but the question is how many levels, right? So you need 1 level or 2 levels. If you look at like the hardware vendors, they will give you estimates for 1 level, like what are the error rates, right? If you talk error rates 10 to the minus 3 or 4, and then you do 1 level error correction, maybe it goes to 10 to the minus 5, 10 to the minus 6, and then suddenly you can run an algorithm that has 10 to the 6 gates.
Yeah, but the clock speed will now be very, very slow. I mean, if you're doing ions.
Yeah, so if you do error correction, of course, the clock speed will also go somewhat down. That's right. So it depends on how much the clock speed goes down as well. But here in the first place, this left graph here will just tell you about we'll disregard clock speed, right? But it's true. The clock speed will then influence how this number translates into actual time. Yeah. Sure. Yeah. We have some kind of like example numbers in the paper of what you can how does it compare with current hardware and so on. There's one point, and maybe it's the last point I'm going to make. Of course, if you're doing this, you also, for quantum phase estimation, you need a starting state. So quantum phase estimation needs a good guess and a starting state. And we investigated different starting states, and essentially it's up to the chemists. So the chemists know very well. They will be in charge of getting a good estimate to the energy and then hopefully deliver a good ground state overlap already. There is then, and then depending on what they deliver, you can look how expensive is it to prepare that starting state. And there's essentially three type of things. We can just say a Hartree-Fock, right? That's the cheapest way of getting a starting state, but you do see that it does decay, the overlap. But the nice things about the algorithms that we looked at here is that they benefit from having good overlap. So if you let the chemists work harder, okay, to get a good overlap state, and you put that in your machine, your quantum algorithm will have to do less work. Okay, so and here is the SOS means sum of Slaters. So sum of Slaters, you see it decays, but then you can do a matrix product state approximations, and those you can also prepare relatively cheaply, but it becomes more expensive, right? To prepare a bond dimension 32 state on a quantum computer, but you have to trade it off, right, against like having to run a more expensive circuit. So there will be this trade-off. But we did have an entire study where we investigated if we can get good starting states, because there was some literature out that said, look, good guiding states, good initial states are difficult to prepare. We believe it should be possible. It should not be the bottleneck, but you will only know at the end. All right. Here's my concluding slide. Thank you for the attention. We developed a complete modular autonomous computational pipeline for free energy calculations. It's compatible with traditional quantum chemistry and future fault-tolerant quantum computers. One thing I haven't mentioned yet, but it can adapt to the computational resources, right? So you can scale this quantum core. It's not like a given size. It's like, you can scale it, you can try out. The modules can be exchanged or upgraded. We demonstrated the feasibility of this whole pipeline on this ruthenium drug protein complex. It's difficult already, but it shows the whole thing works. And the multi-layer embedding and plus the machine learning, it reduces this quantum region, and it should make kind of built around make quantum computing for these free energies feasible. Yeah, it's open source and free. If you're interested, just email us and engage with us. Okay, thank you for the attention.
Thank you. Thank you for the talk.
Thanks for the great talk. Are there any questions? Marco, I see your microphone is on. Do you have anything you want to ask?
No, I just want to thank for the talk.
I see.
So I have just like a question about what type of computers, I mean, I mean, you would need like an order of tens of thousands of fault-tolerant Toffoli gates to get something here?
I think I think it's all like the question, what kind of statement you want to make at the end. All right, you want to make a statement like, you want to have quantum advantage. You want to go to a regime where you cannot, where your classical system is completely out of bounds, or do you want to go to a regime where you can match it, or a regime where you may have quantum advantage? So I think it's a slider. I think somehow it's a little bit up
More or less
to
to be on the state of, I mean, just to reach even the state of art of classical.
Yeah, but I think it's a little bit unclear what the state of the art is. Also. So because a quantum computer kind of like delivers something different also, right? It gives you like these, it gives you more guarantees on the accuracy, for instance. Now there will be like, if you take this a certain molecule, people will say like, okay, well, for this one, a couple cluster with blah will work. Okay. and then you come with your quantum computer, and you can maybe also do that, but you would be kind of like you would be in some sense you know, of course there will be a moment where you should be able to do something the others can't do at all. Okay. Um, but until that is, I think it will be decided by, you know, comparing to experimental data, or it will be decided when that point happens.
Mhm.
Right? So now you know, now you can say like, okay, so 20 here my favorite. I spent quite a lot of time actually. You could actually, this is this is a really interesting discussion. I recommend reading the part potential for quantum computing. I spent quite a lot of time figuring out what we should write there. So essentially, okay, um, I opted there then for discussing two regimes. One is for 30 spatial orbitals.
Which is like
Okay.
6 qubits or something like that.
Yeah, that would be 60 qubits, yes. Where there is some literature that says that this is a point where it's identified, you know, where it becomes relevant to compare to traditional methods.
Mhm.
Okay, so that puts you roughly in the middle of this graph here. Okay, and then we're talking 10 to the 6. Okay, that implies immediately in the worst case, okay, if you have no like kind of like error compensation and so on, you want your qubits to be at an error of 10 to the -6 to be on the safe side that you can do it.
Right.
Okay, but maybe in practice it'll work when they have an error of 10 to the -5. Okay, so like give or take an order of magnitude here.
Uh-huh.
So then, and that means someone has to give to you 60 qubits, 60 qubits with this error rate. Now they can give you bare qubits that are just bare, like good like this, or they can give you like an error corrected qubits
Right.
that reach at this error correction level, that thing.
Mhm.
That is then that's almost like an architecture question. And then so this will be the first. I think this is the first regime, and then the second regime is when you have like 60 spatial orbitals. Then I think you know, outperforming here, I write for instance, outperforming the MRG will require you to do 60 orbitals. But then you can say, well, okay, outperforming DMRG, but DMRG was only a proxy for full CI. It wasn't really doing full CI. We would be doing full CI. So so I think there's maybe these two regions here, and then of course here the estimates here come to 10 to the -8, right? It would be 10 to the -8 error rates. You shave off, etc., and then the runtime comes into the picture.
Yeah.
So then you have to start discussing like, okay, how fast is your platform?
Right.
But maybe you don't need 4,000 data points. Maybe 1,000 will be enough.
Mhm.
It seems from the discussion with my colleague that hundreds will be not enough.
I see.
Okay, so
But currently you run it with something like DMRG, right? I mean, you're simulating the quantum.
yeah, so currently, you can see in the what was that? You can see it here. So they used in the data. It says it precisely, but but they used it for very small cores.
Mhm.
But you see, this here is unitary coupled cluster, single, double, triple.
Yeah.
And then this NFPT2, I have to look up exactly what they did. But yeah. But my understanding is they did a DMRG calculation. They did DMRG calculations for the system.
Mhm.
But then you see from the active space, they still use the perturbation theory to home in part of the correlations also on top of it. Okay, so you basically do a so So on this quantum core, okay, you essentially select some part, you treat this wave function based method, and then you put, and then you also put perturbation theory on to home more correlations. So there's actually kind of like a layer here, and maybe you would also do that first quantum mechanically.
Okay.
So that you really only treat what they do with the DMRG or these methods, and then you put this other thing on top. We also have have a proposal for an algorithm for these perturbation theory methods, but that's not as realistic. There's one thing I forgot to tell you about. Where is that actually? I'd love to tell you about. Oh yeah, this is hard to believe, but we did a full state vector simulation of this algorithm in order to estimate the Trotter constant for this ruthenium complex. And we used Marek Miller, one of my postdocs here. He programmed a extremely fast classical simulator that can run on HPC clusters, both CPU clusters and GPU clusters. And we ran it on a CPU cluster at ETH Zurich and on as a pilot project on the new supercomputer of Denmark that Novo Nordisk and the state have bought together. It's like number 21 GPU cluster in the world or something. And it was running there. It was quite cool. So if you're interested in full state vector simulation, have a look at phase 2, which is what our program is called.
Okay, thanks.
Yeah, thanks a lot. If there are no any other questions, let's thank the speaker again. Yeah, really thanks for your time. Yes.
Thank you very much.
Thank you.
Thanks for having me. If you have questions, just send me an email. I'll try to relate to the experts.
Yes.
Thank you.
Thank you.
Bye.